So earlier I'd said the Richardson I'd said that total error for trapezoidal is proportional to x square delta x square. Okay, well, that's just the that was just the first term. It turns out that the total error I is actually I1 plus C1 delta x square, right? So this is the estimate, and then we stopped here. We said C1 delta x square. That's the error, but we really ignored some other terms. So it turns out that there are trailing terms which we ignored. So that's the actual error in the trapezoidal rule. Okay. Now what we did was for Richardson an extrapolation, we assumed I is I1 plus C1 delta x square, effectively ignoring the higher delta x4 and so on. Okay, and so then we wrote, if you have another step size, you can write it like this: delta x1 square, delta x2 square, and then based on these, you can write I equals I1 r square minus I1 divided by r square minus 1. Okay, so this is just a recap. This is what we did for Richardson, but we know that the total error has, these higher order terms. We have not only this, which we took in Richardson, we also have delta x to 4, delta x to 6. So now the question we have to ask is, well, what we're trying to do here is, here the total error after using I is proportional to delta x raised to 4, which is no surprising because this is the term we ignored. Now the question is, can we get even more accurate solution by using Richardson extrapolation recursively? That is, trapezoidal has an error of delta x square. Richardson gave us delta x is to 4, but can we now start doing this trick where if the error here, okay, is so to explain what I'm trying to do, let me do one thing. Let me just rewrite this like in the following way. Let me call that 1 comma n equals r square I 0 comma n minus. Okay, so what I did was, let's assume that the first step of an iteration you're doing is the 0th iteration. You use step size n divided by 2. Okay, and that gave you something at iteration 1, right? Now we could actually now write this as I1n is
that I0
comma n, yeah. So we use this trick to get an improved approximation, which is accurate to delta x raised to 4. Now, what we can do is we can use it again. We could say that I2n is r square I1n minus I1n divided by 2 r square minus 1. So note, I've done the same formula, except that I've changed the iteration number from 1 to 2. And this will come out. So this one was accurate to delta x raised to 4. It turns out that this will be accurate to delta x raised to 6. Yeah, this is basically exploiting this formula a second time and a third time and so on. There's an error here. This should be, my bad, this should be r raised to 4. Yeah, that's right. Okay, so this would be accurate to delta x raised to 6. Now we can just keep repeating this. Each time you use this recursive formula, you'll get even higher order accuracy. So delta 6 will be delta x raised to 8 and so on. So let me write that down. So we can keep repeating this calculation. Derive a general expression previous iteration k minus 1 minus I. Because that encompasses all the Richardson extrapolation, but carried out iteratively. Okay, so this calculation is done iteratively till we have something like this, k minus 1n. So I computed iteration k minus 1 minus kn. I computed at iteration k, the absolute value is less than some tolerance. User chosen tolerance. Okay, for example, 1e negative 4 will do. So you're ensuring that the 4 decimal places doesn't change between successive iterations. You can actually pictorially depict this 0, 1. So I'm going to show you the same iteration using this sort of a tree type diagram. 0, 4. Eight, need some more space. 0, 16. So let's say you do this calculation for step size 1, 2, 4, 8, 16. Okay, next you use Richardson extrapolation. So Richardson extrapolation will give you I1, 2. For that, you'll use these two values. Okay, using this formula I wrote down earlier. So this is the formula I wrote down. You have to use this formula. It'll give you I1, 2. You'll get accuracy of delta x raised to 4 for the trapezoidal rule, and of course higher for the Simpson. Then do this for 1, 4. You'll use this value, this value. Then you do it for 1, 8. Then 1, 16. Okay, if you're not happy with the accuracy or it doesn't converge, you can do this again for I to 4, which will use these two values, I to 8, these two values. One 16, 216. Okay, then you're still not happy with the accuracy or you don't get convergence, you can do this again. And then the last one you can calculate here is 416. So if you use the trapezoidal rule, then this part is accurate to square, this part is accurate to 4, this part is accurate to 6, this part is accurate to 8, and this part is accurate to 10. So you get delta x is to 10 accuracy. So this is like a remarkably good accuracy, right? Delta x is to 10. So the more calculations you do, the higher accuracy you get. So there is like a trade-off. Higher accuracy means more calculations. But you only go, so let's say that you chose n equals 2. You only need to go all the way to 8 times what? 2, 4, 6, 8, sorry, 2, 4, 2, 4, 8, 16, 32. You only need to do calculations for 32 grid size. That's about it. You don't need to do anything better than that, but you can get this accuracy if you do this chain of calculations. So these calculations typically are less time consuming because they involve fewer computations. Just calculate this number, right? So all these are not, this part are obtained from the previous values. So only these ones you need to do trapezoidal calculations. Calculations based on previous iteration. Okay, so one problem on this, and that would be it. So let's see how to use this. Something like this, and there will be a problem in the homework. You probably want you to do the calculations, the initial calculations for the first iteration, just using a Octave or MATLAB. Sometimes it's just too time consuming.
Wow, pretty much. We have homework due this Thursday.
No, there's no homework. There's nothing posted yet, but I'll post one today. So it'll be due next week. Okay, so here's the problem. Okay, so why would you use quad in MATLAB? Is when you don't know the solution to the analytical, the integral analytically. If you don't know the analytical solution, quad is a way of giving you the answer. So you could use quad. The syntax would be something like this. You'll define a inline function 4 divided by 1 plus x squared. So you're expected to put this in MATLAB or Octave. And then to get the I exact, just say quad F, A, B, and then you put the tolerance 1e -8. That's it, just 2 lines. Okay, the answer is 1. It's actually pi. The answer is pi. 3.14159. You know the next digits of pi? Does anybody know? 1415926. What's after 26? That's all you know.
This is like,
I see. I know many engineers and mathematicians use pi exponential. You know what the value of exponential is? 2.76 something. E raised to 1. 2.71828. Yeah, so many people in science and engineering and math use pi and e to set their passwords. So if you want to crack a password, you go to first try 3.14159, 2.71. It's very common. Was that? That's not mine. No. No, I was. And I don't have experience breaking password, but I think that's you might see that in movies or in books. If you've read about Richard Feynman, the Nobel laureate who got a Nobel Prize for physics, he was good at picking locks. There are like a couple of books on his memoirs, which I would highly recommend. So it turns out that you can actually integrate this equation analytically. Do you know what the integral of 1 divided by x square? Okay. When I was in high school, I had to memorize that. It is tan inverse of x. So when you take the limits, 0 and 1, I think really pi by 4, yeah, pi by 4 minus 0, right? Oh, it's 2 pi. Wait. I think 1 plus 1 divided by 1 plus x square is tan inverse of x. Yeah, it is tan inverse x. So what's the answers don't match? Oh, it is pi divided by 4. My bad. Tan inverse of 1 is 10 pi. Okay, that's right. It's pi. Okay. Okay, so I just have like, okay, so this is more like I did this pretty much in Octave and then just put the numbers here. I will provide you with the code which is used to generate the solution. So it's a lot of writing essentially, but hopefully you'll get the idea once I write it down on paper. So Romberg integration. Let me do it on a new page because there's a lot of space for this. So iteration 0. I put n equals 2, and I have a code which will give me the solution for trapezoidal rule. And I put n equals 4 in the same, it's just a matter of replacing n with 4. And I ensured that I printed 8 decimal places. So by default, Octave only prints 3 or 4 decimal places. 3117647, n equals 8, n equals 16. What's wrong? 0, 4. 2.1389. 8849. 141.42989. Okay, all this is using I also did 32, by the way, because I wanted 16. So 3.14. Wait, I've messed up something. This is what happens when you write things down. Okay, this is for the one below. This is for the one below, and then I'll change this 3.14094161. So this is trapezoidal rule in octave. Okay, so this is what we've done so far. There's nothing new here in computations of these 6, 5 values. Okay. However, when you go to iteration 1, this is where you'll use the Richardson extrapolation formula. So I12 is 2 square I0, 2 minus I0, 1 divided by 2 square minus 1. Then I14 will be 2 square I0, 4 minus I0, 2, 2 square minus 1, 1, 8, 2 square I0, 8, 0, 4, 1, 16 is 2 square I 0, 16 minus 0, 8 divided by 14156 63 159 50 and 141. So you can see we're already getting close. 59265. Actually, that's the right value to 8 decimal places. And that's just doing one iteration. But we've already got, like, you can see here, we already got 4 decimal place accuracy right here in this iteration itself. Okay, so just to complete it, I'll just do the remaining iterations, but you don't have to really go all the way down. If you use the criteria, which basically checks successive iterations, right? Checks this with this. So sorry, checks this one with this one. And you can see that it's not accurate to 8 places. If you subtract the 2, it's not 1e negative 8. So then let's do another iteration. Iteration 2. I 2, 4 equals 2 raised to 4 I1, 4 minus I1, 2 divided by 2 raised to 4 minus 1. I2, 8 is 2 raised to 4 I2, 8 minus, sorry, my bad. It's 1, 8 minus I1, 4. 2, 16 is 2 raised to 4 I1, 16 minus 1, 8. 2 raised to 4 minus 1. Okay. Okay, there are 3 of these, so they are 59409 159, 266, 3.14159, 265. Okay, we can actually check it now. So we have I116, and we can check it with I216. So if we check I116 minus I216, we get it is less than 1e 10 raised to negative 8, right? Because it comes out to be, I've only carried 8 decimal places, but it matches. So, so that is the solution. Our approximate solution is 3.14159,265, which also happens to be the answer which we computed using exact integral to 8 decimal places.